Prim's algorithm is one of the algorithms for finding the minimum spanning tree of a graph. A minimum spanning tree is obviously a tree, and a tree is a graph that is connected and contains no cycles. A spanning tree is a tree that contains every vertex or node on the graph, and the minimum spanning tree is therefore the spanning tree that connects up all the vertices or nodes of a graph using the arcs or edges of least weight in total. On the screen you can see the 4 steps that Prim's algorithm uses, and often with these algorithms it's much easier to see it in practice rather than just to read the steps, but the steps are there nonetheless. So step 1, you just choose somewhere to start. Now normally in an exam situation you'll be told which vertex to start, and that's just to make it easier for the examiners to mark. Step 2 is you connect that start vertex to the nearest new vertex. Everybody gets that bit right. You just look for the lowest number on the arcs coming out of the start vertex and choose it. It's step 3 where you need to be alert, because you don't just then carry on daisy chaining around the graph. The spanning tree can grow out of any of the vertices that you've chosen so far. So step 3, from any vertex on the tree so far, add the shortest edge that connects a new vertex. And that's important, we'll come back to that in a second. And step 4 is you just keep doing that. So we're going to have a go at using Prim's algorithm to obtain the minimum spanning tree for this graph. You can see this graph has lots of edges or arcs, they're sometimes called, that have got really low weights on, and hopefully Prim's algorithm is going to use those. Prim's algorithm is an algorithm that does work every time, so it should, and what we're going to do is when we do it, we're going to start at the bottom. We're going to start from vertex E. So if we just move that over to one side, we say that if we start from vertex E, the first edge that we choose is going to be the 2, because the choices were 2, 3, or this long one around the outside, this 7, so clearly 2 is the lowest. Now at this point we need to be careful, because we're up to step 3 of the algorithm, and it can now grow out of this vertex at this end. It could choose the 3 or the 7, or it could grow out of this vertex at this end, and it could choose, or that 2's already been picked, so it could choose the 3 or the 2, and out of all of those, the 2, the 3, and the 7, the 2 at the top's the least, so we're going to add that one. Now you can see that we've now reached this point here on the graph, and clearly this 1 coming out of this end is going to be the lowest. Now it's at times like this you need to be a little bit careful, because you're looking and you're thinking, oh, the 3 is less than 5, but remember it can grow out of any of the vertices that we've chosen so far. And actually if you look at this one on the original graph, there's a 2 coming out of there which is less than the 3 and the 5 at the top. So we're going to pick that 2. Then there's another 2 coming out of this one. There aren't any other 2's or lower anywhere else, so we're going to pick that one. We've nearly connected everything up. There's just these 2 bits at the top, and we can get to those by any of the existing places. So we can come from here with a 4. We can go back to this one and we can join that with a 3, which is less. There aren't any 2's left on the diagram, so we're going to pick that 3. And then finally to get to here, it's a choice of using the 4 or the 3, so clearly we're going to use the 3. You can see that this is a minimum spanning tree. It's a tree because it contains no cycles, there's no enclosed regions. All the empty space, if you like, is on the outside of the lines. There's nothing that's enclosed. So you can see that it's a tree because it's got that kind of spidery appearance about it. And you can also see that it's a spanning tree because you just compare across to the graph on the left, and you can see that all the vertices are included in this graph that we've drawn. So it's a minimum spanning tree because we've used Prim's algorithm, which always produces a minimum spanning tree. Adding those up, it's normal to give the working and the actual lowest weight that you've been able to obtain as part of your solution. So the lowest weight here is 15. In terms of the additional working that you might be expected to give on an exam, the graph will probably have the vertices lettered, A, B, C and so on, and you'll be expected, as part of your working out, before you calculate the minimum total weight, as well as drawing a diagram of what you've got, to write down the order in which those vertices were added.